Okay, well, I didn't mean
I
to
fully
be-
understand that my brain works in weird, kind of pointless ways.
It's not weird, pointless ways, just roundabout ways.
Yeah, weird, pointless, jump from here to there ways.
It's,
I'm okay with
it's
that.
I think I was saying that, like,
Oh, I know.
you always give an answer, and it's not always, it's usually the right answer, it's just not how I would go about it.
A right answer,
Yeah.
B right answer.
Yeah.
That's fair.
Good one. Alright, so quickly, review here. Let me see if I can come up with something off the top of my head. Alright. All three of these, I want you to determine if, when I take these salts and put them in solution, if it'll be acidic, basic, or neutral. I'm not asking you to find what the pH is, I just want you to tell me, will this create an acidic solution, a basic solution, or a neutral solution? Not yet, but yeah, eventually. Got an answer yet? No, I'm not asking you for you to just, I just want to make sure everyone's thought about it. Everybody, please give it a thought. Yeah. Okay? Who thinks they know this one? Raise your hand.
Make it acidic because HF
It's basic.
basic. Okay.
Right?
Okay.
This is the negligible one because that would produce a strong base. Okay, this is the conjugate of a weak acid.
Okay.
So it's a strong base, it will react with water to produce OH. Okay, next one. Anybody? It'll be difficult to do the ice table problems if we can't even figure this out. Figure what's neutral. Are they both neutral? Or one neutral? When I say neutral, what do I mean? When I say it has neutral properties, what am I talking about? When I said this was neutral,
Strong, so it doesn't dissociate.
okay, it's an ion that in water won't react because it would produce a what? Something strong.
Yeah.
Okay?
HCl is strong.
It's a strong acid.
So
Okay, HCl is a strong acid, that makes that guy neutral. Because chlorine isn't going to react with water because what would it produce? Strong acid, which is never together, right? It's always apart. So it's going to stay apart. It's not even going to react. Okay? This guy is the conjugate of a weak base. Yeah? NH3, weak base. So this is going to be acidic. What about this one? We had some work to do.
well, HBr is a strong acid.
Neutral.
Isn't KOH a strong?
Neutral.
I figured it'd be neutral because it's being left.
You figure, but that's when I throw the
Right.
switch at you, usually. Okay? You're trying. So do you see how important it is to know what the strong acids and strong bases are? Because you got to be able to identify their conjugates. And remember, the difference from the conjugates is simply just a proton. Okay? Then, what we did we first stated that if you have ions that both the anion and the cation are neutral, that would produce a strong base, KOH. That would produce a strong acid, HCl. It's going to be a neutral solution. Same for all of those. They would produce either a strong acid or a strong base. If you put it in water and dissolved it, that's going to give you a neutral solution of a pH of 7. Then we did, I think, the basic, we did basic or acidic? What is it? We did the basic form, where you said that anytime you have cations that are neutral, right, these guys are not going to produce or react because they would produce a strong base, and whose anion is a conjugate of a weak acid. Okay, I gave you an example of an anion that was a conjugate of a weak acid when I gave you this. There's an anion that's a conjugate base of a weak acid, and we know conjugates are opposite. So if I have a weak acid, the base is going to be relatively strong, and that's why when you have this situation, you're going to get a basic solution. And we did a problem like this, where we had this completely dissociates because it's what? It's ionic. It's going to give you your full set of ions. This won't react because it produces a strong base. This is a conjugate of a weak acid, making it a strong, relatively strong base. Okay, we had to do some work, didn't we? Okay? Let's flip the script a little bit. I think my example was NH4Br or something like that. Okay? Salt in which the anion, this guy, okay? Not a base. I would have just said it's neutral. Okay, this guy's neutral properties, which means it's not going to do anything, it's not going to react, not going to affect anything, because that would produce HBr. Okay, that's going to have no effect. But whose cation is a conjugate of something weak. Okay, that's the conjugate of a weak base, NH3, making that relatively strong from an acid standpoint, producing an acidic solution. Now you could memorize all that, but just be able to identify what is the neutral part. And then think about if it's acidic, because a lot of times if you look up here, they'll give you which one's important. I can tell you right now that this is probably the guy that's not neutral, just by that.
So is one of them always neutral?
One of them won't have to be. Well, no. I'll explain that at the end today. But most, for like the problems you'll be doing that aren't just conceptual problems, like I'll show you a couple conceptual problems where I'll give you two ions that are conjugates of weak things. And you'll have to figure out what is going to be the strong, or which one's going to be the dominant producer. But we'll get to that. That's a great question. We'll get to that after a couple of these problems. Okay? So in this guy, okay, it pretty much just gives it away by telling us what the Kb is, which means this is the guy that's going to produce something. This is not why. HCl wouldn't form, so that guy's going to have no effect. And so what we're doing here is dealing with NH3 or 4. That's in water. This is plus. What is that going to act like? It's going to act like an acid. So if it's going to act like an acid, I'm going to need the Ka, correct? They didn't give me the Ka, but they gave me the Kb of its conjugate, so we can do what?
Divide by 1 times 10 negative 14 divided by 118 times 10 negative.
think it's 5.6 times 10 to the negative 10.
Yes.
Okay. There's my KV. Everything's a 1-to-1 ratio. So x equals square root times your initial concentration, which my initial concentration, why is it going to be 0.1?
Says that as the concentration.
But technically, like, this is the salt's concentration, right? So all salts dissociate completely. So I have 0.1 of both of these things. Doesn't matter that I have 0.1 of the chlorine because the chlorine isn't even going to react. Why? It's really weak base because it's the conjugate of a strong acid. Yep. Right? That gives you an X of
7.4, 7.5, and negative 6.
okay.
But you just did the square root because you knew it was a 1-to-1 ratio.
Yeah.
And then those are 0.
Be careful. Eventually, next chapter especially, we'll be dealing with things called common ions. What we're going to be dealing with is an acid with a salt in it that has a common ion of that acid. And so you're going to have initial concentrations over here. So, yeah, we're slowly going to add a little bit, a little bit, a little bit. Okay? Now, I can tell right now that this X is extremely small, and this concentration is not small enough for the 5% test to be anywhere near 5%. Can you guys make that connection in your head? Okay, I can give you what it actually is. If I don't even have, yeah, I didn't even write it. I just wrote valid. Okay?
Yeah, it's 0.007%.
Yeah, 0.007%. Yeah, that's not even going to be close. Do you have a question? Okay, so what am I going to do with this? Now this is where you had to think a little bit on the last problem we did yesterday. But in this situation, what is X? It's this.
Which is H plus.
Okay? In the problem we did before, it was our OH minus, and then we had to do a little bit more to find pH, correct? So all we have to do in this situation is take negative log. And that will give us our pH.
5.13.
Yep. And there's the pH we want. Here we had a salt where the anion was neutral and the cation was a conjugate. Okay, conjugate of a weak base, so it gave us a relatively strong acid, and we have an acidic solution. So you can just dissolve salt, some kind of salt that isn't neutral, and create it to be acidic or basic, depending upon what salt you're dissolving.
So is table salt neutral, or is it
It's
acidic?
neutral.
Okay, that makes sense. Yeah.
That's going to produce a strong base. That's going to produce a strong acid. Yep.
And no.
That's why table salt's quite useful in a lot of ways.
Why it's.
I mean, that's one reason of the many reasons why it's the salt that we use a lot. We wouldn't want it producing acidic
Well,
or
the
basic
sea
stuff.
salt isn't necessarily NaCl, right? Is it?
I don't know that. I have no idea. If, I would assume it would just be
I mean, there are other
salt
in
from
it.
the sea.
Well, I know, but I know there are other.
I don't think it
salts
tastes
in
much
water.
different. Do you?
I don't think so. A little bit, but not a lot. That could be just plant debris.
All right. Salts in which the did I go backwards? Yeah, I did. All right, here's a second type of salt that is a little bit unique, and I want to show it to you because it could show up on your test. I think we talked about this at the very beginning of the chapter when we were just identifying acids. Do you remember the aluminum guy where we had aluminum in it with the water, and I broke it up into, it was kind of a goofy one. Okay, these guys are going to act as an acid. And I'll show you again the equation here. First off, when we go back to our original salt that we put in solution, which one is neutral? Which ion? The chlorine is, because it would produce HCl. Okay, well the aluminum, the heavy metal aluminum, is not neutral. Okay, because it can surround water, create this heavily charged ion, which is willing to give off a what? Yeah, it is. Yeah, it was a while ago, but I'll write the equation here for you. It's kind of goofy. That's why I wanted to make sure I show it. Because when it reacts with water, it gives you that with this left over. We go from 6 to 5, and an OH, and one less charge. One more charge. Okay, does that look familiar from the beginning of this chapter? Like it was like one of the 5 ones we did.
Yeah.
That was kind of unique and different. Okay, this is going to act as an acid. And they gave us the Ka value for it, so we don't do any flipping or changing or anything. Is it a 1-to-1 ratio?
Yeah.
And we can make some quick approximations. Initial concentration is there. There's our Ka. Initial concentration of 0.01. There's our X. Now I would do the 5% on this one. It's probably going to be valid, but this is a much these are much closer that it's worth checking to make sure that it's a valid,
It's 3.7%.
which is close. Okay, which means our X is actually going to be valid and makes our, and which is our H plus concentration. We finish by doing what? Made a lot of that. Gives you a pH of
3.4.
questions. I went kind of fast through this. I'm kind of, doing the quick, simple method of assuming square root and whatnot. Just make sure you do a quick check, make sure everything's a 1-to-1 ratio, make sure your products don't have any concentration, and then yeah, it's fine to just do the quick way if you'd like. But still, make sure you check to see if it fits the 5% test, because if it doesn't, you are going to have to go back and do the quadratic. Okay? All right, last thing from this lesson, this is where Grant asked that question about, well, what if there's a situation where neither of the ions are neutral? Then what do you do? Do you guys know where that table is that has all the K values?
14.3. What it was.
Where are you?
Page 6.
Page what?
660.
662? Oh, it's nowhere near it. Okay, that's not the one I'm looking for. 644. Go there. Now we just had a couple. We could go to that if we need to. Okay? So if you look, this and this are both conjugates of weak things. So are these two. And so are these. Okay? So one will act as an acid and one will act as a base. So the way to figure out if this is going to be acidic or basic solution would be to look to see which one is stronger. Does that make sense? So what you're going to have to do is, okay, this is a conjugate of a weak acid. This is a conjugate of a weak base. Okay, so this will act as the base. I want to find the Kb for that. And this is a conjugate of a weak base, making it an acid. I want to find the Ka of that. Now, did I, in this lesson, give any of those? Okay, so we're going to have to look it up. Ka of NH4, is it in there? Looks like it is. 5.6 times 10 to the negative 10. Now this isn't going to be in the acid one, but is the conjugate going to be? So I could find the Ka of its conjugate, take that and divide it from 1 times 10 to the negative 14 to get your Kb of that, correct? So let's see, where is its conjugate? There it is, 1.8 times 10 to the negative 5th. Take that and divide it from your Kw. You should get actually this. Which means this guy's going to be what? Neutral. Kind of goofy. Everybody understand that?
So is the acid always first? Like that's the conjugate of a weak
Yeah, so yeah, this is the conjugate acid of a weak base. Always the cations will be conjugates of bases. Whether they're strong or weak is, you have to figure that out. Okay? And the anions, and that's why there was that beginning, all those bold things that I had. That's what that's kind of saying, but it's kind of a mouthful.
If it's not one of these 6, then it's just weak.
I wouldn't say, oh, yes, yeah, yep. But you also got to think about the 9 strong bases too.
Yeah.
Yep. Okay, so in this one, we already got the Ka for it, so I don't have to relook that up. We can find the Kb of Cn minus, and I'm guessing they give the conjugate of that. The conjugate of that is relatively weak, which means that this is probably going to be relatively strong. I'll give it to you. What is it? 1.6 times 10 to the negative 5th. So what will this be? Basic. What's that we got? 44 of this. Perfect. Everyone following why that's weak? Or not weak. Sorry, why that's basic? Anybody have questions on why that's basic? Okay? I gave you when you have a heavy metal aluminum in there, just in the previous problem. What was the Ka of that? .4 times 10 to the what? Okay, that's a relatively strong acid. If it were my guess, I would say this is acidic, but it's always safe to check. Okay, and so we're trying to find the Kb. That's a 4. 2 minus. So that would actually be the conjugate of HSO4, which I think is in here as well. And HSO4 is really strong, which means SO4 is really weak. So this would be weak, this would be strong. I've got to say. Okay? It's a lot. A little, I mean, it's assuming at this point that you have the strong acid is understood well, strong base is understood well, so that you can apply some of this stuff. Okay? Questions? Okay, here's what I'm going to do. We should be able to get through the next lesson short. I do want you to do 14.8's homework. I'm not going to require you to do 14.9 through 14.11's homework. Okay, it's not a requirement. If you want to do it, you absolutely can. Are there going to be some conceptual questions on it on the test? Probably. Okay, but I'm going to be sensitive that if you're just like, I can't, that's up to you. Okay? Questions on that? All right. The next lesson is heavily conceptual. Should go relatively quick. So what we want to discuss here is kind of some structural effects and why some things are strong and other things are weak. Is there a reason based on its structure? Is there things that we can figure out based on electronegativity and bond strength on how to determine whether something is going to be a strong acid, strong base, or something that's weak? Okay? So for example, if I wanted to compare why this is an acid and this is nothing, why is it that the bottom one has a hydrogen and can give it off, but the top one has a hydrogen and is not willing to give it off? There's a couple things that we're going to talk about that determine whether or not it will give it off. Okay, there's really two things that you'll see on the next slide. It's the strength of the bond, okay, also with the polarity of the bond. Okay, so if I were to do the Lewis structure, can you guys in your head know what that Lewis structure is going to look like? The hydrogen bond is a carbon-hydrogen bond, and here we just have our hydrogen-chlorine bond. Okay, there are two factors that are the main factors, not the only, that affect its ability to give off that hydrogen. Okay? If you were to look at this, what is one significant difference that you could maybe point out pretty quickly? Yes. Okay? This is pretty polar. I mean, I wouldn't call it extremely polar, but I'd say it's very polar. How about this one?
A little bit less so.
Pretty much non-polar. I mean, that's a little bit polar, but they're so close in electronegativity values that we could pretty much just say it's like 2.1 and 2.2 or something like that. Yeah. Okay? So polarity has a big impact on it. Also bond strength. Okay? This guy's actually a fairly strong bond. And this one's weaker. Now, here's the thing that's really important. I'm going to pull this up on the next slide. Okay? Why would polarity be important when figuring out if it's going to act as an acid or not?
How would associate?
Yeah. Why would it being polar cause it to dissociate well?
Stronger charge, stronger carbon there.
Remember this? Like dissolves like. What are we dissolving it in?
Water.
Water. Okay? If you have something that's really polar, it's going to be more attracted to the water, giving water a stronger ability to surround and break it apart. Okay? How would the strength of the bond affect whether or not that's going to break apart? What would you think? Strong bonds break easy or weak bonds? Okay? So the nature that's going to likely make it an acid is something that's high in polarity and something that's low in. If you have high polarity low bond strength, you're likely going to get a strong acid. If you're somewhere in the middle, it depends. It's probably still going to be a weak.
Why would HCl be a strong acid if it has a greater difference in charges?
It's very polar. It's good. Okay. So, I do want you to open your books 677 quick. Uh, 677. I think it gives you the hydrohalic acids. Yep. Okay. And you remember how we have that goofy HF, which is like the only, not only, but the one of the halogens that doesn't produce a strong acid, but the other three do. And it has to do with the relationship between polarity and bond strength. Okay? The difference in polarity between HF all the way down to HI is not significantly different. Yes, is HF more polar? Absolutely. It is. Okay, but is it significantly more polar than the other guys? Not really. Okay, so all of them you could say have a relatively high polarity. And the reason why HF is not a strong acid is because it has the strongest bond of all of them. And so there is kind of a little tipping point. Okay, are we going to get into where that line is? No. Okay, but it usually high polarity is good, low bond strength is also good. However, typically high polarity is the result of stronger bonds. So there is a breaking point. We're not going to have a fine line on it. Okay. Next, oxyacids. Do you remember what oxyacids are?
Yeah, oxygen.
Oxygens involved in something that's acidic. Okay? Usually the result of oxyanions, which are a lot of times found in your polyatomic ions, or are your polyatomic ions. Okay? It says the acid strength increases with the increasing number of oxygens attached to the central atom. Flip the page. You got another table, 14.8. Now let's just focus on the top half where we have the oxyanion series of Cl with the oxygens. Okay? The very top one has, with all four oxygens, is one of our what? Oh, it's one of our one of our 6 strong acids. Then you can see that it's got a Ka value that's uncomputable and really large. And as you lose oxygens, what happens to the strength of the acid? It goes down. Here's why. Okay? What do we know about oxygens? Well, that's probably a pretty broad question because there's a lot you could probably say about this, but oxygens are really electronegative. Okay? So if you look here, the one with the 4 oxygens has a bunch of oxygens on the right side that are all really electronegative. What that does is starts to pull on all the electrons to it. Okay? And because of that, what that's going to do is it's going to significantly weaken because of these oxygens pulling electrons this way, it's going to significantly weaken that bond and make it more polar. And from an acid standpoint, is that going to make it good acid or bad acid? Good acid. Really electronegative, pulling electrons this way, making this bond more polar and weakening it in the process. Hence why that guy is one of our strong acids. Okay, but if you remove a few of these, we got something like this. Yes, is this still pretty electronegative? Yeah, but it's not going to pull quite as much. Not going to make this quite as polar, not going to make it quite as weak. And so therefore, it's going to be a weaker acid. You can see that on the bottom series as well, the bottom 2 sets. Okay, so the general rule when you have an oxyanion series is more oxygens Okay, more polar bond, weaker bond, that's gonna make it a relatively stronger acid. What? This is what that was saying, I already stated that. So the X is saying is it could be anything. It could be, you know, chlorine with oxygens, it could be bromine with oxygens, it's whatever attached to that OH. Alright, last, well, okay, there's technically two more things. These are not as important as the first couple of things I stated. This is heavily conceptual. I would do you some good to read this short section on 679. What this says is you have essentially acidic oxides and basic oxides. It's things that have oxygens in them that act acidic or they act basic. Usually what you have here is your acidic oxides tend to be covalent and your basic oxides tend to be ionic. For example, a basic oxide that you probably are why don't we just pick this up tomorrow quickly before we review everything? And then we'll have it all covered, taken care of. I don't want to try to, it's going to take more than 2 minutes. Okay?
I want to check the history.
So, I'll get you to your history. Don't want you to miss out on that.
Well, Fisher always has economics and